All right, today we're actually going to be talking about section 3.8, but I just want to do a quick section 1.1 review of some functions. So what is a function? We've been down this road before. A function f is a rule that assigns each element x in a domain to exactly one element, f of x, in the range. And this has been worded very particularly. Each element x in a domain being mapped to exactly one element, f of x, in the range. And when it's worded like this, we get something called the vertical line test. And a graph represents a function if and only if it passes the vertical line test. So we can see that here on the left-hand side, we've got the graph of y equals x squared. If I draw a vertical line somewhere, I'm only going to cross over my function the one time. Whereas if I have x squared plus y squared equals 0, when I draw a straight line, a vertical line, I pass through my graph twice, which means this graph on the right-hand side does not represent a function, but rather an expression. And why is this so important? We'll see in just a minute. So section 3.8 is on implicit differentiation, and oftentimes expressions aren't given to you clear and concisely. Sometimes we don't get things that are nice. So an example of an explicit relationship is y equals x squared. And that one's pretty easy to see why it's explicit. But often relationships are expressed implicitly, so think x squared plus y squared equals 1. And that is, in order to get something that looks like y equals something on the right-hand side, we're going to have to do a lot of legwork to isolate y, and in fact, we can do that. So we see when I have my function set up as x squared plus y squared equals 1, I do not pass the vertical line test. And so it does not represent a single function. However, we can solve for y to get explicit equations. So here I just do the work to solve for y, and y equals plus or minus the square root of 1 minus x squared. So when I have y equals square root of 1 plus x squared, I have this red graph here, and it passes the vertical line test because I can draw a vertical line and only cross my function once. And then we also get y equals negative square root of 1 minus x squared, and that's going to be this blue graph here at the bottom. And we do our vertical line test, and we only cross once, which means it's a graph of a function. So now that we have our function representation for y equals positive square root of 1 minus x squared and y equals negative square root of 1 minus x squared, we can find their derivatives pretty easily. But are we always going to be able to do something like that? The answer is no. So for y squared plus x squared equals 1, it's pretty easy to solve for y. But this is not always the case. Sometimes it gets much more difficult and you can't isolate y. So how can we find a single expression for the derivative directly from an equation without first solving for y? And the answer is using a technique called implicit differentiation. And whether or not you need to exactly know the name of this, not very important, but being able to use the technique is very important. So what exactly is this technique? And I'll show you using an example. So here I want to find the derivative of x squared plus y squared equals 1 with respect to x. So what I'm doing here is treating y as a function of x. So we write x squared plus y of x, quantity squared, equals 1. And then I'm free to differentiate on both sides. And I get ddx of x squared is 2x. And then I apply the chain rule, which we just talked about in our last video, to y of x quantity squared. So the derivative of my outside is 2y times the derivative of the inside. And I don't really know what's going on the inside. I just know that y depends on x. So we're just going to call it y prime. And we know that the derivative of a constant function is 0. So now we have our expression. We solve for y prime. And that's going to look like So we have y prime equals negative x over y. And you can see that when you do implicit differentiation, your result is usually x's and y's on the right-hand side. So y prime is a function of x and it's a function of y. So let's use this result. So find the slope of the unit circle at 1 cubed root or square root of 3 over 2 and 1/2 minus square root of 3 over 2. So we know y prime, which is the slope of the tangent line, is equal to negative x over y. And since it depends on both y and x, we plug in y and x. So I plug in negative 1/2 times 1 over my y, which is square root 3 over 2, so I just flip it for the reciprocal. My 2's cancel out, and I'm left with negative 1 over root 3. And that's for the first one. For the second one, we do the exact same thing. Y prime equals positive 1/2 times negative 2 over root 3. And the reason I'm including the first negative sign, this one, is because I've got negative x over y, and I'm including the second negative sign because it comes from here. Again, my 2's cancel out, my negatives cancel out, and I'm left with positive 1 over root 3. And what does this look like? Well, conveniently, I've got a graph here. So at the point 1/2, you can either map to positive root 3 over 2 or negative root 3 over 2, and they're going to have corresponding slopes. So the slope at 1/2 square root of 3 over 2 is negative 1 over root 3, and the slope at 1/2 negative root 3 over 2 is 1 over root 3. So that's what this looks like, and that's how we can find it. So let's move on to an example. Now this one is a little tricky, and I'm just going to include this one. I'm not going to include any from the homework, but if you have any questions about the homework, feel free to email me, because this one is a pretty tricky example. So again, we're going to rewrite sine of x times y of x equals x squared plus y of x. Now we're going to take our derivative. So for the left-hand side, when we take our derivative, we've got to use the chain rule. So we take the derivative of the outside, which becomes cosine, leave the inside, and then take the derivative of the inside. And the derivative of the inside, we have to use the product rule. So the derivative of x is 1, so we get left with y, plus the derivative of y, which is y prime, and we leave x. Luckily, on the left-hand side, it's a little bit easier. We just have 2x plus y prime. So now I'm going to distribute these on my left-hand side because I have y cosine xy plus xy prime cosine xy equals 2x plus y prime. And my goal is to isolate y prime. So I'm going to move everything with a y prime onto the left side of my equation and everything without a y prime to the right-hand side. And I'm even going to factor out my y prime to start with. And that's how we solve for y prime. So this one was kind of a complicated example. We had to use the chain rule, we had to use the product rule, and we're doing implicit differentiation. But this is the sort of question that you can expect to be asked of you on maybe an exam. By the way, our exam is coming up next week. I am going to post an exam update to tell you about what's going on with the exam and a review, which I hope to have done at some point for next week. And and then we'll be able to take the exam. It's going to be the exact same format as the previous one, but it should hopefully have questions that all work without having to download anything or anything like that. All right,